Hey, what's happening, guys? We're back talking about transformers again. Here's the same hand-wound transformer we used last time. This is the primary. This is the secondary. On the primary side, we have the input from the function generator, and we have channel 2 on the scope, and on the secondary, we have channel 1 from the scope. So what I'm feeding into this is a sine wave. Let me get some adjustments made and we'll take a look at it. Alright, I got our scope all set up here, and I know you're not seeing much now, but play along with me and we'll figure it out together. So I'm inputting a sine wave at 500 hertz, 1 volt peak to peak. Again, the blue channel is the primary, the yellow channel is the secondary. And if you look, you can see we do have a very slight amplification here at 500 hertz. So let's look into this and see first about waveforms. How do they make a difference? Okay, so now we have a square wave. And once again, you see at our 500 hertz, a definite amplification. We're up to almost 5 volts. There's our triangle wave. And you can see we have dropped down below our 1 volt input to 960 millivolts. Ramp. There is a negative going ramp. And you can see even with the negative going ramp that we do have an amplification in our peak-to-peak voltage. So the shape of the waveform is somewhat important. Here we are back to square wave, which is my favorite. And there's sine wave. So the only thing I'm changing right here is the shape of the waveform. There's sine wave, there's square wave. So let's go back to sine wave. And in this case, we're going to change our frequency. Let's go up to a kilohertz. Alright, so now we're at a kilohertz, and our sine wave, we're showing 1.4, let's call it 1.5. So we're seeing a 1.5 amplification there. Let's bump up nothing but the frequency this time. Okay, now our frequency is 5 kilohertz, and you see we're almost at 2 volts peak to peak. So there is some definite amplification going on there. Let's take it up even higher. 50K. Now at 50K, we're seeing 2.6 volts. And you can see some sort of a traveling wave happening here. But remember, the blue is our input, the yellow is our output. And we can zoom in here and look at the waveform, so you can always see what's happening. But I like to look at it like this for the simple reason that it gives us just an overall picture. Input, output, and you can see there's definitely some noise happening there. Alright, so let's go back. We'll keep it at 1 kilohertz. So you saw the effect of frequency on the sine wave. Let's change our waveform. I want to find the right button. Okay, square wave. Now we will change our frequency. So there's 1K. All right, now we're up to 50K. So you see we're having overall the same effect. The amplification is, of course, different, but the effect pretty much remains the same. So we're seeing the effect that frequency plays in our role. So there's our 1 kilohertz square wave. We're getting a nice amplification of a little over 4 times. Now, here's the one thing you're going to notice. Our input and our output look to be closely matched here. And that's, I think, mostly an effect of the impedance, the way the transformer is wound and where the probes are placed. All right, so now there are some questions about what actually constitutes AC and DC. And that has a lot to do with what you consider to be the zero crossing point. Let me do something here. I'm going to change our offset, which is right now at 0, to 1 volt. Okay? So now we have, actually that's a 0.1 volt. Hold on here. Okay. So now we have a 1 volt DC offset. But because we are AC coupled here, everything remains the same. I'll crank our offset up 2 volts. 3 volts. Now you can see that our amplification changes, but everything still functions. Now we're back to 0 offset. Let me try and explain to you why that's happening, if you don't already understand it. If you do, you can skip all this part of the end of the video. Alright, so finding a pen here. 0 volts, right? Let's say this is 10 volts. And this is minus 10 volts. Now, our waveform. Regardless of whether it's a sine wave or a square wave or any type of waveform. This is only talking about AC. We're not talking DC here. This amount, this quantity right there is our potential. And it can be the same here or here. This amount does not change. Okay? The potential of all 3 of these waveforms is exactly the same. The only thing that is changed in this entire graphical demonstration is a point of reference. So here is our absolute reference, our 0 crossing point. But when we're dealing with an AC waveform, every time it switches direction, it creates what's known as a virtual ground, its own 0 point. That's why you have to have your grounds connected together when you're doing a circuit. Otherwise, there's no frame of reference. You have to have a frame of reference if you want, we'll call this waveform number 1, number 2, and number 3. Without a frame of reference, waveform number 1, number 2, and number 3 are equal. If we use 0 volt as our frame of reference, well then in that case, this becomes what? 4 times higher than this one? And 8 times higher than this one? But that is all based upon our frame of reference. And that's why we connect our grounds together to give our circuits a frame of reference. Without that, it really doesn't matter where it's crossing 0. The transformer itself doesn't care where it crosses 0. Again, it will create its own virtual ground. So I hope that helped explain things a bit better, and I hope you enjoyed this. If you did, please give me a thumbs up. Feel free to comment, share, and don't forget to subscribe. Big thanks to all my patrons. That's it. I'm out. Peace.